Okay, so let's have a look here at the loading and that occurs uh, in the gears and the stresses it causes, and of course the damage that causes. So when we have the pinion coming into contact with our gear, they're acting here at a particular angle. So we break that up into two components. We're going to break that up into the radial, the downward, and we're going to break that up into the tangential. Now the tangential is the one that we're worried about. The radial is, the radial doesn't do anything really. It presses the two gears against one another. That's about it. The tangential is what allows the gears to transfer the torque from one another. It allows for the transfer of power. So as for that power, for calculating it, our power, so our rate of work, uh, when is equal to the force that's being the tangential force that's being transmitted, and basically the velocity of the contact of those at that point. So how how we got one the pinion coming in this way, we've got the gear coming in this way. They're meshing together at a particular velocity in the middle. So it, if we want our power in horsepower, then we can plug in our velocity in terms of feet per minute and our tangential force in terms of pounds. Multiply those two things together and divide by 33,000 to get our horsepower. Because again, 1 horsepower is equal to 550 foot-pounds per second. So that's multiply that by 20 for a minute if we got our v in minutes. So as for calculating the v, that velocity, pi times the diameter times the rotational speed in RPM will give us the v in terms of feet per minute. Again, keeping in mind we want to keep our pitch diameter there in feet. So usually it'll be given in inches. So you may want to you divide by 12 there. But anyways, so we want to transmit that much power. We're going to be limited upon the strength of the gears. So we're going to have the gear teeth. They need a certain amount of strength in order to basically ensure that the strength is, so the surface doesn't wear away, and we got the volume strength or bending strength here. Here, let's go to the next slide here. So basically, when we get the gears coming into contact here, we get a stress field that arises. So at the point of contact, right in the center there, you've got compressive stresses occurring. So those cause surface fatigue here. That surface fatigue is going to, it's wearing away of the face of the gear tooth. And then that compressive stress, we're pushing this way. Obviously, if we're pushing this way, then what we're going to be doing is we're also going to be causing a bending moment. And that bending moment is going to cause, over here, it's going to cause more compressive stress. Over here, we're going to cause tensile stress. So we're worried about what's going on right there, right? We're worried about what's going on in the corner with the tensile stress because alternating tensile stresses, such as when a gear tooth comes into contact with another gear tooth, gets loaded and then unloaded, is going to cause you to get fatigue damage. So we'll start off with that. So the bending stress, the calculations for kind of how the bending stress caused them was done by Lewis and the end of the 19th. Why did I put ST? Anyway, 19th, not 19th, anyhow, 19th century. Um, so based upon a few assumptions, the loads applied to single tooth. So back then they didn't really have they didn't have precision gears that where you could like get load sharing. So basically the assumption was that kind of the tooth came into contact all at once. So the entire load was kind of applied at a single tooth at once. So you always got a point where the maximum load was at the end of the tooth. The radial component of the loading is negligible. It's certainly always going to be less, at least with the angles of the teeth that we're working, and the pressure angles that we're working with. It's certainly going to be less than we would see uh, for the FT. It's also not really causing any damage. So like this causes a bending moment. This that doesn't. Yeah, so we're not too worried about that. The assumption is that the loading is uniformly distributed along the tooth face width. So again, perhaps not the best assumption, but that's kind of the calculations were derived by based upon that assumption, and as we'll see later, it was later refined to take into account when that didn't occur. And then we got our sorry, we got negligible friction resistance and negligible stress concentration effects, which probably wasn't a very good assumption. But again, this is done back in the day before they really had a good understanding of how the stress concentration worked. So the bending stress that occurs, that's fairly simple. We got a load applied at the end of the tooth. We got a moment arm here, so the force times that H is going to give us our moment. Here, MC over I. I'm sure you all have recognized that equation. So our C here is going to be T over 2. Our I here is going to be T to the third times H divided by 12. Our MC here is going to be F times H. Plug all that together and you get that. So the problem here is essentially kind of when you get into the actual loading, the loading doesn't actually occur kind of at the end of the tooth, and we don't know what this T here is. So basically, they rejigged the geometry here to kind of sub out this T value here, replaced it with this X here, and got rid of the H as well. So the H and the T are both going to be functions of the geometry. So if you can replace those with with this single X value, and then that X value is just going to be a function of the geometry. So essentially, that will be based. This will be what we'll call the. This allows us to sub in what we call a Lewis form factor, which is again, it is a function of the geometry. It varies based upon the number of teeth we're talking about for the tooth in question. So basically, they're just they just rejigged the original formula that had two variables that we didn't necessarily know, and we're plugging in a single variable that is applicable, kind of that stands in its place. So if we're working in imperial, our stress is the force times the P, our pitch, divided by B, and our form factor. So again, P is going to be in units per inch there. If we're working in metric, essentially we're using the gear module instead of the pitch. So again, gear module is in units of millimeters. So obviously it'd be on the opposite, it'd be on the bottom of the equation instead of the top of the equation for the pitch because it's inverted units. So the Lewis form factor, that y there, is kind of it is a function of the number of teeth and the pressure angle. So yeah, it's and again that's just basically kind of the ratio of the geometries that we're talking about. So you just go ahead and look up. If we're looking for a 20-degree, then we are working with this line here. If we're using stub teeth instead, then we're working on one of those dotted lines there. But that having been said, yeah, slight difference between the full depth teeth and the stub teeth is going to result in a slightly different y. But so again, some of those assumptions that we talked about weren't necessarily valid and kind of overlooked some aspects. They're fairly important. So they took that and they refined it. So the modern equivalent of the Lewis equation has some corrections. So when you have really high speed transmissions, then you're going to get kind of the teeth coming together. If they're coming together at a high speed, then that kind of counts as an impact loading. So that's going to cause a bit more stress than would have otherwise occurred. You can have good accuracy or you get a poor accuracy. The contact ratio. So when you have a higher contact ratio, you're going to be able to share the load amongst the teeth. So basically, what that means is that if you have a particular if you have a tooth here, let me oh, what am I doing here? If you have a tooth and that's a terrible looking tooth, but anyways, so if it's not sharing the load at all, then the contact will occur at the top. But if it is sharing the load, then basically the initial contact will occur while the gear is still in contact with another tooth. So basically, some of the load shared. So the maximum bending moment is actually going to be caused when the other tooth comes out of contact with that gear. So that's the point where the whole load is being carried by the one tooth, but basically that contact occurs at lower down on the tooth, so there's less of a bending moment that occurs. Now, obviously, stress concentration comes into play. We got got the corner, we got the fillets there. They're going to be causing stress is going to be higher there than we would have calculated based upon just kind of the classic beam bending approach because of the stress concentration effect. When you have overloading, so essentially if there's kind of variation in the load kind of supplied to the gear or variation in the variation in the load that the gear's driving or variation in the kind of the torque from the motor, then you're going to basically going to be causing a lot of acceleration and deceleration occurrences. So basically that'll spike up the maximum stress as well, which again causes fatigue damage. And then when you have poorly mounted gears, then basically let me just sketch this real quick. So if you have a poorly mounted gear, so if you got a gear tooth, here's the face, and maybe it looks like this. So if your gear tooth is such that basically, you know, if it's kind of a bit crooked and you are kind of only getting contact over here, and there's no contact going on this side, then basically you're going to see a lot more stress down in this corner, uh, where the below where the contact's occurring, and there's going to be, of course, negligible stress, or certainly less stress in the corner below where you have the poor contact, or less contact. So having precisely mounted gears and having very stiff stiff supports for the gear decreases decreases the stress levels that you'll see, because you're not going to get that variation. Okay, so here's the original form that we took. Here's the form that we're going to take now. Obviously, the FT is the same, pitch is the same, B is the same. This Y got replaced with this J, and then we added a few K's here. So we'll talk about those. So the J factor, the geometry factor, is the Lewis form factor corrected for stress concentration effects and corrected for load sharing as well. So if we, so there's a line here for down here for if you don't have any load sharing going on. So basically, if you don't have a precision gear, then we can't, a very precisely ground gear, then basically we can't assume that they we can't assume a contact ratio above 1, basically, is what's going on there. So if we're making the assumption that the load is applied at the tooth of the tip, then the J factor varies only with the number of teeth. And again, I'd like to emphasize, also point out that this chart is only for the 20-degree full depth teeth. But if you do have some load sharing, so basically if when the gears come together, one tooth comes in contact with the one pair of teeth come into contact while the pair of teeth in front of it are still in contact, then we're getting less. We're the point of contact where the entire load is carried by the one tooth shifts down the face of the tooth. So having a higher geometry factor is going to be better because we're dividing by that amount. So it functions based upon not just the number of teeth for the gear pinion that we're looking at, but also the number of teeth in the mating gear. So if we got 1,000 here, or we have 17 down here, so on and so forth. We got this kV, velocity, dynamic factor. So again, that's based upon the tangential speed. So like I said, as we get the rotation, we've got the teeth kind of coming into contact with one another, and if they're going really fast, then that can kind of be considered to be impact going on. Still, relatively smooth impacts, but still impact nonetheless. So that factor is a function of the pitch line velocity. So this chart's in feet per minute, and again, that's calculated based upon with the V's pi times the diameter in feet times the what am I talking about here? Times the RPM. And then it's also a function of how precisely made the gears are. So if we're using a form cutting hob, and we're using this line here, shaping cutters here, precision shaved and ground here, high precision shaved and ground here. So yeah, just so that's figure 15.24 in juveniles. And here's some values that can be used to estimate what those will be based upon what type of method was used to produce and finish the gear. We've got the overloading factor. So this is kind of based upon the degree to which kind of you're getting pulses in the power supplied to the gear and pulses in the power used by the end user. So if we have uniform power and uniformly used driven machinery, then it's 1. If we don't have any pulsing whatsoever, then we're not worried. If we've got some sort of combination of light shock and or light shock, moderate shock, or heavy shock for our power and or our users, then that ramps it up. So going from 1 over to 2.25 for like a combination of a medium shock power source and a heavy shock load. So so if we're talking power, an electric motor is our classic uniform power. Most steam turbines or gas turbines would be considered light shocks. And some hydraulics. Medium shocks, multi-cylinder internal engines. Heavy shocks could be considered if we have a single-cylinder combustion engine. So yeah, that's possible too. But if we're going for the load that we're using, the driven machinery, so like a uniformly loaded conveyor belt would be considered uniform, centrifugal pumps, stamping machines, so on and so forth. Moderate shock or woodworking machinery, mixers, heavy shock, stone crushers, excavators, heavy distribution pumps. I don't know. You got any gears in a jackhammer? That would be a good example of a heavy shock. And then our load distribution. Our M is for mounting, our mounting factor, quality of mounting. So this is a bit of trying to assign a number to a sort of qualitative analysis. But if you got really bad mounting, so you don't actually have full face contact, then we're looking at something over 2.2, and you should probably do some more analysis to get a better idea of what that is. But if you have accurate mounting, small bearing clearances, minimum deflection, precise gears, then it varies based upon how wide your gear is. So from 1.3 up to 1.8 for 16-inch plus gears. You got something in the middle. It's not all that rigid. The gears aren't all that accurate, but you still have contact across the full face. It's still in contact all the way across, but it might not necessarily have your pressure distribution be equal. So that'll vary from like 1.6 to 2.2 for the large ones. Obviously, yeah, so that effect, if you have some slight, some slight displacement in the angles that you're working at when you press things together, the bigger the gear is, the more pronounced that effect becomes. Is basically what's going on with the face width size there. So that is the stress that we're occurring, and we want to make sure that the stress is less than some sort of strength value in order to figure out what our safety factor is. So what sort of strength value should we be using? So what's going on here? Yeah, so we're getting spikes in the stress level that occurs as the gear turns, right? So basically two factors that two situations that could occur. If your power, if you got this gear connected to a shaft, power is coming from the shaft and then being transferred to another gear via the teeth. Then on this gear and on this gear, the stress distribution looks like that. It's the gear in the middle where the gear is just transferring power from one gear to another, which you call an idler gear. Then you're getting spikes. You're getting tension and compression in turn. So guess what? Yeah, that's going to be fatigue. So we're looking at the fatigue strength of the tooth. And of course, most of this should look quite similar to what you've seen before. We're adding a few terms. Shocking, I know. So our SN prime, endurance limit of the material. SU divided by 2, or again, oftentimes you see this coming up in gears more often than not, because oftentimes the strength of the gear is really just, they just tell you what the Brinell's hardness number is. So generally speaking, the Brinell's hardness number divided by 4 will give you your ultimate strength in KSI. So that's and we'll talk about this in a bit, but you may be told different values for like the core and the surface. Use the core because we're expecting these cracks to propagate from the surface to the core, so damage occurs. Damage occurs not just on the surface, so we're going to be using the core value here. We're talking bending, causing the fatigue, so that's a CL of 1. Shouldn't be too surprising. For our gradient factor, that's going to be 1 if we got a pitch over 5. And we're going to use 0.58 if their pitch is below 5. Again, keep in mind that as the pitch goes up, the teeth get smaller. Surface parameter. So surface parameter is based upon the fillet at the root. So, how well was this thing? How well was it? I'm not quite low enough there. How well was this corner right down here polished or ground? So if they don't specify, just assume it's a machine surface. Beyond that, you're just still looking it up on the same table in Chapter 8 of Juveniles that you've been using. Reliability factor, obviously, it's going to be familiar. I don't know why. I don't know why they don't just use CR like they do for everything else that needs to do with fatigue. I don't know why they changed the nomenclature to KR for gears only. It seems silly to me, but whatever. So, anyways, yeah, we're using these values here. So 99.9% is commonly required. So we're often using the 0.753. Temperature factor. So temperature factor uh, will depend upon steel. Your steel gets weaker kind of as it gets heated up, so more damage will be caused if you're hotter. So if in operation this thing is kept below 120 degrees Fahrenheit, then our KT is 1. Otherwise, we can approximate what our KT is based upon this formula here. Again, plugging in our temperature in Fahrenheit. Okay, so the next one is our mean stress factor. So basically, this is going to account for whether or not the gear is seeing the up-down stress, or tensile and compressive. So if it is an idler gear, then our then we use 1, and if it is not an idler gear, so so that the stress level only spikes and doesn't get compressed, then we are left. Then we basically kind of artificially bump up the strength of the material by 1.4. Realistically, I don't know why they don't take this into account in the stress calculation instead of the strength calculation. It's beyond me because this has nothing to do with the materials. This has nothing to do with the gear itself. This has to do with how the gear is moved. You can't. I don't. This irks me. So I'm just going on a rant here, but if you're calculating the strength of a gear, the strength of a gear, this is the strength value for that gear. And then it changes depending upon if we take that gear and put it here instead, where it's an idler gear, versus if we put it here, where it's a driven gear. That's stupid to me. But anyways, yeah. Artificially bump up the strength if you're keeping, if it's not an idler gear, basically. So that is our failure criteria for volume strength or bending strength or fatigue. Yeah, fatigue due to failure due to fatigue crack growth in your gear teeth. So we take this, and that needs to be less than our strength value divided by our safety factor. 1.5 is typically sufficient to ensure a good reliability. So yeah, that is strength due to bending. So we'll talk about contact stress in a bit.